Hello, everyone, and welcome once again to Pavement Matters, which is the Pavement Management Services podcast, where we discuss all things pavement engineering, and also the future of pavement as well. And today we've got a very special guest star, although he's not really a guest star. He is part of our data services team at Pavement Management Services. So you are a star, perhaps not a guest. But it's very good to have you. This is Gadel. He works for us in the data services team. He's currently a PhD student as well at the University of Sunshine Coast. He's recently here from Russia as well. He's been here for just over a year or just under a year, where he carries with him a master's degree in highways and runways, as well as postgraduate research courses in theoretical mechanics. So it's very good to have you here, Gadel, and welcome.
Thank you. I'm glad to be here as well.
Lovely. Now, the actual thing we're going to be discussing today is your research in skid resistance, particularly on runway pavements. And this is something I understand that you actually did a speech on recently at the Australian Airports Conference in Melbourne. So how'd that go? Are you good at public speaking?
I'm trying my best all the time, but it was just a short presentation, and I didn't actually cover many topics in it, and I'm just hoping that we'll be able to discuss it here. So I will speak out everything I wanted to say. So yeah.
Oh, well, that's good. You are in the right place, because despite what our marketing team says, they say I've got a strict time limit, but I don't care. We're going to discuss it for as long as we want to today, and it's the editor's job to make it short. She didn't like that. Cool. So so I guess the perfect place to start is in 3 minutes. What really drew you towards this topic, and what do you find it so interesting about it?
First, I worked mostly with asphalt previously, and I also did some postgraduate courses in theoretical mechanics. But despite the fact that I did those courses, I'm not the best specialist in theoretical mechanics, and skid resistance and my previous topic I studied in Russia, which was the pavement wear. Those topics, they are not bound to any strict mechanical limits, and it's just from the tribological point of view, it's some behavior in contact between tire and pavement surface, and it's just it has a little bit more freedom in that, in studying and researching, and it's a little bit more empirical. It's a little bit harder to fit it into a model, and I'm just used to it, and I liked it a lot when I found out about that project, about that position at the University of Sunshine Coast. I applied straight up without even thinking about it, because it's funny. It's funny to study.
Yeah, no, that's good, and you certainly picked a very good time to start this line of study as well, because especially in Australia, over the last, let's say 5 years, but probably a lot longer than that, airport maintenance and safety has really risen in prominence, and a lot of sort of smaller airports that I think might have been able to fly under the radar for a long time. Not to say they weren't doing anything properly, but now I suppose Australia's trying to modernize, and a lot of these runways that were built sort of as far back as like World War II as sort of training or staging areas, and now they're having to bring themselves up to the modern age, and skid resistance is a very important part of that, because it's the kind of thing that could be perfect 1 year, and after 3 years of 30 planes a day landing in the exact same spot could actually become a little bit of a concern. So yeah, that's the topic of our discussion today. Could you provide some comments on that?
Skid resistance, it's simple to say that skid resistance is really important for the runway maintenance, but it won't cover every aspect of that. But skid resistance is basically ability. It manages the ability of the plane to stop. That's all. So to properly understand the role of the skid resistance in the runway maintenance, you may need to just take a look at the excursion statistics, maybe runway excursion statistics, and it will probably give an answer to the question of how important it is. And probably that's the
okay. So just to be on the same page, so is runway excursion, is that's like when the plane sort of doesn't stop and goes off the runway, isn't it? Okay, yeah, all right, cool. Yep. I've seen some air crash investigation, so I figured. Okay, so is that, so when skid resistance is low, like how important is it for, like there must be other factors at play as well when those incidents happen, or is skid resistance like a really big part of it?
And that's a good question, because that was starting for probably 3 months or so, because I was reading investigations from Australia, from USA, and I also read some studies on that thing as well, because runways, they are made to be long enough for the plane to be able to stop even if there is a rejected takeoff, or if there is something wrong with other conditions and it's really difficult, and it also depends on the winds, on a lot of factors. And in ideal situation, if plane lands right in the beginning of the runway, then everything goes fine. It's really hard for the runway excursion to occur, but the skid resistance, it becomes really critical in the cases where not everything is fine. And from all of the runway excursions, and there are lots of them, not so many in Australia, it was around 45, and in USA it was even more. By even more, I mean that was 2000 or something. And for example, in Australia, 22% of all runway excursion have insufficient braking, lack of skid resistance as one of the influencing factors. In USA it's a little bit lower, but there is also a problem with the data provided by the Transport Safety Bureau from USA, because they don't their investigation reports are really short, and it can be more, but basically it's around 20% of all runway excursion, they happen because of the insufficient braking. And the point is, out of those 20%, probably around 20% of those 20%, they happen only because of the insufficient braking. So everything is fine, plane lanes almost perfect, but for some reason brakes doesn't work, and other 80%, they have wind problems. So the plane has a tailwind and it's just harder to land already, and it also has an insufficient braking. It's sometimes it's just an awareness of runway conditions, and that's actually one of the key factors related to the airport and runway management, because it's not only about the pavement itself, it's also about the control of runway conditions. And that's also one of the factors. For example, pilot thinks that everything is fine, he prepares for the normal landing, but for some reason the runway is flooding, or there is an ice or something. And I mean ice for the USA, not for Australia, of course. And sometimes it's just a malfunction of brakes, but even with the malfunction of brakes, skid resistance is really important. Probably all planes, I mean, at least commercial flights, they have anti-skid systems for the normal braking, but even if anti-skid system doesn't work, skid resistance is still important, and with all of those contributing factors, skid resistance is like a key point that affects everything else. For example, if we try to improve the control of the runway conditions, it's still important to, I mean, even if we report that the runway is wet, the runway is flooded, the proper skid resistance, it's removing that negative factor, if you can say it like that, and it makes the flight and the landing especially safer and better. Yeah.
So I suppose when you really boil it down, a lot of aircraft excursion events, a lot of them are caused by things that we can't control. Things like ambient temperature, winds, even like the maintenance of the plane. Like obviously that's something that can be controlled, but it's generally not the responsibility of the airport to do it. But skid resistance is one of those things that can absolutely be controlled. And it seems like it's a very big part, up to 20% of all incidents involved some sort of element from skid resistance. So what kind of things are we doing in order to improve skid resistance, and how do we know when to improve skid resistance? Like what point is what is the intervention level for skid resistance generally?
So that question actually it's a little bit wide, because how do we know and when do we care? When do we start to care? It's both of those are really long topics, but let's start with how do we know? So in current runway management practice, there are two ways of controlling the skid resistance from the actual pavement side. It's controlling the texture and controlling the actual friction, but by actual friction I mean the continuous friction measurement. And if it is a little bit simpler with controlling the texture, and as everyone knows, the texture is not that simple as well. It has different levels. There is a micro texture, which is a texture with the lower wavelength. It's like a texture of each singular aggregate, and there is a macro texture, and which is improved, for example, by grooving or using the different types of the asphalt, such as SMA or porous courses. And controlling macro texture, in that case, it's quite simple. There are a few methods. It's a sand patch test, grease patch test. It's not used that much, and I don't even think if it's used at all. There are circular track meter, like profilometers and stuff, and it's still simple. And even without it, it's easy to spot if the texture, if the groove is deformed, if the groove is broken, the groove edge, or then if the groove is closed. But there is another part of the texture which is a micro texture, and measuring the micro texture, there is no method recommended by ICAO at all, and the only method they mention is tactile and visual assessment, and it's basically just touching the runway to see how thick is rubber contamination and how smooth is the surface, and that's all. So when we talk about the management of the pavement properties from the texture side, it's only the macro texture measurement by all of the methods mentioned, and they have some requirements for the macro texture, and those requirements, they were it's 1 millimeter of the macro texture, if I'm not of mean texture depth, if I remember it correct. And this value itself, so from the other point, when do we know that the texture is bad, and why do we think that the texture is bad in that case? That 1 millimeter value, it's based on the trials. So what they did, they checked the probability of the hydroplaning when the runway is flooded, and they checked the ability of the pavement of the surface to drainage the water under the tire, and that data is and since it is about the macro texture is really easy to understand by the modeling. It's easy to model, it's easy to do the experiment, and that 1 millimeter value, it's a solid value for to know for sure that the skid resistance from the macro texture side is provided properly. And if it was that simple, but it's not that simple, because we still have the micro texture, which is the other part of the texture, and we cannot control it from on the pavement. I mean, we can control it. There are methods, like a lot of methods. It's the profilometry, 3D scanning, even. It's just stereoscopy. If we take two images from the microscope, like standing a little bit aside from each other, they will work like eyes do, and they can pick up the texture difference. And so yeah, there are lots of methods, stylus-based method and like that, but none of those methods is used in the actual runway maintenance, and none of this method is recommended by ICAO. What they do and what they use is continuous friction measurement, and continuous friction measurement is just an imitation of the actual braking of the plain tire on the runway, and that imitation is made by just pulling, dragging the tire. Simply, yes, it's just dragging the tire that is partially braked. It's like 15% braked, and we just look at the dragging force from that tire, and we get that friction value. But when we imitate the friction like that, it's still we don't give an answer how good is the aircraft braking. What we have as an answer is how good that particular tire of that particular continuous friction measurement equipment, how good does that particular tire brake. And braking itself, friction itself, it's a really complex topic, and as I mentioned earlier, it cannot be modeled, it cannot be calculated just by using any computational power. It's because it can be wet, there can be dust, even without any wetness or dust, it's still slight change in the speed or some previous skid. For example, if we That's how the entire skid system works. If you avoid any skid at all, you have the better friction. If you have a little slip, your friction immediately drops, and it's a really complex topic. And when we do the continuous friction measurement, we just answer how good that actual tire brakes. And another part of the question is, how do we know which level of the friction for that particular tire corresponds to the better friction for the plane? And it's a really complex question. So that they just conducted a lot of experiments. They tried a lot of times. They tried a lot of times with planes. They did it in NASA. The whole continuous friction measurement is actually based on the USA studies on NASA, and not only NASA, but there was a big project, and I don't remember all the institutions that were the part of it. But yeah, basically what they did, they compared a lot of continuous friction methods to each other. They compared to the plane, and that's how they got all of those levels. But the other thing, they did it 50 years ago. Probably 50 years ago, it's 70s. It was 70s, closer to 80s. And they did it 50 years ago. And 50 years ago and now, the planes are different. And the runways are different. Everything is different. And when we talk about the continuous friction measurement, we need to take into account those differences. I mean, it was really different even before that. Even then, they were compared to the planes back then, but now the difference it's even bigger. And so yeah, that's how do we know how to measure the actual skid resistance, and not the actual skid resistance, but and how to know when it's bad.
Yeah, and I mean it kind of makes sense really, because when we conduct these scientific experiments, they're almost always done in a vacuum. But this is a very practical, very real life assessment, and there's just so many different, like you sort of touched upon it, that macro texture. We've known for years how to test macro texture using things like the sand patch, which, by the way, anyone not in the know, sand patch is literally you pour sand onto the pavement until all of the little gaps between the aggregates are all filled up, and that's how you know how much the texture depth is. It's a very, very low-tech assessment of texture depth, and we've got systems these days that can digitally model that through laser profilometers as well. So yeah, but things like that have been known for years upon years, and that's easy because macro texture is relatively easy to understand. But when we go to micro texture, we're talking about the actual shapes of the individual aggregate stones, and that's like asking someone to count the number of jelly beans in a jar. Like, if there's so many different variables at play, so many different possible things that could happen. One little patch of runway could be markedly different from another patch of runway 300 meters down, and yeah, it is, I think, perhaps one of the reasons why we don't have any pardon me, accepted ways to measure microtexture is just how complex it would be. Oh, I've got something.
Yeah, about the microtexture and the sand patch test. And you're saying that it's simple and it's basic, and we have more advanced method, which is the digital just profilometer. But the thing is, the microtexture itself, the only one of the main purposes is the drainage. And even the sand patch test, I mean, it's an old method and it's simple, but it's not that bad, because when we talk about the drainage properties of the pavement, not all of the microtexture paths, the paths for the water to escape, not all of them are open. And the laser profilometers and everything, and the profilometer itself, it picks up only the open gaps, only the open texture, and there are still closed some closed pores that still work as a drainage part, but they are impossible to be picked up from the profilometer. And even if that method is simple and old and basic, it's probably not the best, but it can give the answer that we cannot obtain from any other methods, and it's just funny. Sorry to interrupt.
No, that's okay. No, yeah. When I said it's rudimentary, it's one of those like, oh man, I can't believe it. Like it's I can't think of another example, but yeah, it's so crazy that something that was done 50 years ago is still probably the best way of doing it. And I guess you are absolutely right with you've got a physical object. I mean, sand is different from water, obviously, but it will flow roughly like another physical object like water, because they're both physical. But when you're measuring things with laser, I suppose there are some things that are missed like that. I suppose the advantage of laser really is that you can scan the entire runway sort of in one go, whereas you would need probably an entire beach worth of sand in order to do the same thing with the sand patch. So yeah, I think probably a good way to sort of get an accurate measurement is probably a combination of the two, or maybe focus the sand patch on areas that you know might be suspect. But yeah, as you said, it's even though the method to determine it may be simple, there are just still so many variables. Sort of coming back to the plane side of things now, you said using continuous friction measurement device is all well and good, but it's still not a plane, and there's lots of things that planes have to consider that isn't really a consideration of the continuous friction device. Point being is that the continuous friction device has a very specific tire. It's a tire manufactured specifically for that device, and only that device, so that when you measure multiple runways side by side, you don't have a variability in your measurement. But planes aren't like that in real life. You might have a Cessna, you might have a Learjet, and you might have a Boeing, and they're all going to have different size tires from different manufacturers. They're going to have different compounds.
So you mentioned tires, and there are indeed requirements for the continuous friction measurement from the tire point of view, and they are really strict. But there are still some range, and there were studies that stated that within that range of the tire, there is was it 10% of a difference in the friction measurement results or something? Even the friction is so difficult topic that even within those ranges for that continuous friction measurement, there is such a big difference, and it's also it raises the question about the proper understanding of the continuous friction measurement results and the proper interpretation of those results and using it for plane and everything. Yeah, that was I just wanted to add.
Yeah, no, yeah, well, I mean, yeah, that's entirely it. When there's this much variability, it sort of turns it away from being an exact science. Engineers love to deal in exact sciences, and depending what kind of engineer you are, is going to affect how successful you'll be in your pursuit of exact sciences. But I think with skid resistance, it's very much not an exact science, is what I'm getting from you. But ultimately, it is something that you can control, even if you can't definitively measure to the nth degree that we would like to. So what are the kind of things that airport managers can do to control skid resistance?
From the pavement point of view, it's just controlling the texture and right interpretation of the continuous friction measurement results. Because when I work in the lab back then in Russia, I worked in the lab that was controlling all our labs in our region that were working on the highway construction, and in basically all methods of any laboratory method for the pavement control, in all of these methods, there is always a room for you to make your results better, and it's actually funny how I talked to some of the people who asked me, and me and those people, we have just studied together and we were friends, and they had their own labs, and they just asked me how to make the results of the testing better, not the actual payment better, but the testing results, how to make them better. And it's important to to remember that we are not thinking about the better results of the test, but about the better pavement. And continuous friction measurement, it's not an exception. There are ways to make your continuous friction measurement results better. And for example, in Australia, most of the local airports, they test their pavement once a year. So what you can do, you just pick the driest, coldest season time of the year, and you do your measurement at that driest, coldest time of the year, and your friction measurement results, they're going to be better. It's simple, because the better the wetter the surface, lower the friction. And even if continuous friction measurement, it's using it's wetting the pavement before the tire, and the pavement is wet, it's still there is still a difference in those results between, for example, summer and winter results, between spring and autumn. And colder, drier the pavement, better the results. And if you do all the testing at that exact time of the year, it's obvious that the summer results are going to be different. And as I said, difference in the tire, it's also really important. And it's really easy to get the better friction measurement results without changing the pavement itself. And the right management in that case will be right interpretation of the results and understanding when the pavement goes bad, if we say it like that, and when do you need to worry about it, and focusing on the touchdown zones, it's obvious, and just looking at the pavement, looking at the rubber contamination, and checking the friction measurement results from that exact point. And it's all really important. And the skid resistance can be controlled, it can be improved, but the right understanding of all of those matters, it really matters.
Yeah, that's actually a very good point, because we did some internally at PMS, we did some studies with skid resistance ourselves, and yes, the temperature is a very, very big part of it. It's a surprisingly big part of skid resistance, not just on runways but on roads as well. And that's a very good point that I think a lot of maintenance engineers and managers may not consider, and that is that if your goal is to improve skid resistance results, then there's other things, like there's things that you can do that could potentially interfere. A lot of our clients who want skid resistance testing done, they do request it around the same time of the year, and I think that's just sort of to fit in with the make sure it's tested annually. But I'm wondering how many are actually considering the real climate effect of doing your testing. Is there anything that you can do as an airport operations manager or anything to ensure that the results you get are the best, and if not the best, at least consistent with each other? Is like sort of the time of year, is that the main thing? Is there anything else as well?
The person who does the testing, it's also really important, because for example, the guy, he just forgot to turn on the water, and you will have the water, the actual water flow is not controlled properly, and it's probably the most important part. It's the person who does the test and the testing itself. But yeah, the time of the year, yeah, it's important. And if, as I said, if you do the test at the driest, at the coldest time of the year, you just give a little bit more room to your results. And ideally, you pick up another time of the year. But if you do it at those seasons, you just give a little bit of room for results interpretation.
Okay. All right. So yeah, actually, that's a good point. If you're going to get markedly different results at the beginning of the year as opposed to the middle of the year, it could be a good idea to do two surveys just to sort of, especially if your intention is to model how skid resistance changes. So actually, one thing I'm not entirely sure about is that how much difference are we talking about between the warmer / drier and the colder / wetter months? Like, I mean, in Australia. Obviously, that's a really wide question. I'm sure there's going to be a massive difference, especially in colder places when ice makes an appearance. But say in Australia, where the difference between temperature is like, say, maybe 15 degrees between summer and winter, is like, in terms of percentage, what is that actually going to do?
I have figures here, and
you have figures. Oh my goodness.
Yeah. And for example, from the study conducted in 2005 in Australia, in Victoria, was it? There is September results for that particular city, because September on the in Western Australia and September here are different times of the year, so it's not it's not a strict recommendation to do the testing in September or in June. So the September results on the middle of the calibration strip show 0.96 friction. Same part of the calibration strip in November. Yeah, in November, probably it's wetter, closer to the in December, because November and December results are roughly the same. It's 0.79, 0.96, and it's an extreme example, but it's not the most of the extreme example, because somewhere at some parts of the graph the difference is bigger, some parts of the graph the difference is small. But yeah, it's 0.2, 10% at least. So 10% of difference in results at least. And so we have 0.26 difference in friction in different times of the year. And if we remember the requirements for the skid resistance results, for example, for the grip tester, between maintenance planning level and minimum friction level, the difference is 10. It's 0.53, 0.43. So it's basically you will get your results above the maintenance level, but there is a risk that they are below the minimum level. It's that simple.
Yeah, man, that's quite a significant difference. I feel like if I was a pilot, that I would probably notice that, possibly. I mean, you've probably got other things on your mind when you're landing a plane than that, but you know, that's pretty. I honestly, I was expecting it to be about maybe 2 or 3%, but yeah, you in the extreme example, that was at least 10,
that's the results
maybe
of the
15.
study. Based on the results from statistics from other Australian airports, the difference is about the same. It's 0.2 in different times of the year in different testing conditions.
Okay, so I guess we'll probably start trying to wrap things up at this point. I think
I would really love to talk about the mechanical and about the more detailed interpretation of the texture results, but from the practical point of view, it's basically knowing the limitations of the method and correct interpretation of those results. It's the key thing. about the proper skid resistance maintenance. It will be a little bit harder to have any practical interpretation of that, but yeah, the friction basically it's also not that simple. It's the way friction happens is part of the tire. It just gets into contact with the part of the surface, and the tire gets stuck to the surface. It deforms, and it goes back into deformation. And actual friction, it happens because of that, because of the tension in the tire and the energy dissipation in the tire. And from the practical point of view, the role of the texture in that process is it just better grabs to the tire. And when you do the theoretical modeling or anything else, it's basically everything is up to that surface depth. But good surface depth and good texture is also one of the way to reduce the effect of the contamination. And for example, with the macro texture, it's the main thing about it. It just provides the better drainage. Same for the micro texture. Better the micro texture, less the influence of the contamination. And knowing that, there is an optimum influence of the micro texture and optimum micro texture. So it's easy to increase the micro texture as far as we can and just put the sandpaper instead of the pavement, or just to push that micro texture. But actually there is an optimum, and I did some measurements. I did some comparisons to the other friction testing methods, and as I said, there is an optimum, and if you go beyond that optimum, you don't get that much of the proper friction. But there is another thing: if you go below that optimum, the friction actually drops really fast because of that, because the micro texture protects from the contamination and gives the friction, and you get the less friction at the same time, and you have the bigger experience, the bigger influence of the contamination, and it just drops. And it's just to state again that it's really easy to miss that moment when the texture is bad, because there is an optimum. You go below that optimum and it drops really fast, and it's just to emphasize the importance of the proper skid resistance.
Okay, so in this case, like if there's an optimum, what happens if you go far and above that optimum? Because I understand below the optimum things get slippy very quick,
Yeah.
but above the optimum, what are the side effects that happen there?
You'll just make it more expensive. That's all. Why do you
fair
need
enough.
to?
Okay.
Yeah, and it's just as I said, it just reduces the effect of the contamination, and the contamination effect is already reduced above the optimum, and all you do, you just make it deeper and make it sharper, and probably you will increase the friction a little bit, and at the same time you will also increase the tire wear and the rubber contamination from that particular tire, and it's just funny. Yeah, the ideal scenario is you have optimum friction that allows you to brake for the longer length, but the length shorter than the runway itself. And it's the ideal scenario. You make your landing as long as possible without affecting the safety. You will have the pavement more durable, the braking better, the wear of the brakes and the tires less, and it's the best way. But it's too expensive to provide such level of the microtexture anyway, so it's just optimum anyway.
Yeah, so it's like diminishing returns. There's no sense to go too far beyond what is required, and I mean that's sort of another sort of cornerstone of engineering. I believe is actually, funnily enough, a Russian general in World War II who said, "Better is the enemy of good enough." I can't remember exactly his name. But it's something that rings quite true even today. Good enough is sometimes good enough. To do it better will just be more expensive, and then sometimes you've got some side effects of in itself. So yeah, I think that pretty much sort of wraps everything up. I'm really glad you came in today, Gadel, or came on, I suppose, because we're doing this online. And yeah, no, it's really good that you've had the chance to talk about this as well, because I feel your pain when you've put so much work and effort into it, and to only get 4 minutes to discuss about it at a conference, it's a bit disappointing. But I hope we've given you all the time that you could ask for today. Of course, do you have any sort of further readings that might be available anywhere, or still something that's a work in progress?
Yeah, it's in progress. But it's just if anyone is really interested in that, he'll be just check the studies, the profiles on the ResearchGate, where all of the published papers are also posted, and it's just good to know sometimes, because I worked from the practical point of view in the asphalt testing for many years as well, and it's always good to know what happens on the research side, because sometimes it's really important for better understanding of your work and for better interpretation of your results.
Okay, fantastic. Well, thank you once again, Gadel, for coming on. My name is Lachlan McLean, and this is Pavement Matters. Don't forget to check us out on YouTube, Spotify, or wherever you get your audio from. You can also follow us on LinkedIn as well. So until next time, we'll see you later. Thank you. Goodbye.